Welcome back. We are in the next lecture of Fundamental of Electronics. In the previous lecture, we discussed on amplifiers fundamentals. We will discuss here the circuits that are formed by amplifiers. Those are basically the operational amplifiers. So operational amplifiers are basically the fundamental building block of any electronic devices. We have discussed very detail about the theoretical fundamental aspect of operational amplifiers, the principle and applications. The basic and special purpose op-amp circuits that we are going to discuss in this lecture are the comparators, summing amplifiers, integrators and differentiators, instrumentation amplifiers, and some of the specialized amplifier circuit like OTA, log, antilog amplifiers. Applications of these amplifiers are basically included in the signal processing networks, the digital circuits, and analog to digital conversion applications. Let us first see the comparators. So these are basically the specialized op-amp circuit that basically comprise of two input voltages. The output is always one of the two state, either high or low. The key characteristic involves very fast switching time as low as 500 picosecond propagation delay, and it has high open loop gain which enable the detection of tiny input differences. These comparators are used for analog to digital interfacing. The zero level detection is one of those comparators. Here the inverting input is grounded. So you can see here the negative terminal of the op-amp is basically grounded. So we say inverting input is grounded or it is at reference. The input signal is applied to the non-inverting input. So we are giving the input signal to the non-inverting input. There is a smallest input difference that drive the amplifier to saturation. So whatever the difference we are getting at the input, this will drive the amplifier to saturation. And hence it can convert the sine wave to square wave, which is known as squaring circuit. So if the input is sine wave, the output that we get it is basically in the form of a square, which goes from minus V out maximum to plus V out maximum. The non-zero level detection circuit, here the fixed reference voltage is replaced ground at inverting input. So if you see here the inverting input which was grounded, now a battery is connected. So it is known as non-zero level detection, and the other terminal, that is the positive terminal or the non-inverting terminal, is given the supply. Three reference voltage methods we can use it. Either we can connect a battery reference or we can connect voltage divider reference like R1 and R2 connected with respect to the supply. This is known as voltage divider reference. And voltage divider reference, we can apply the voltage divider rule to get the voltage reference, which is R2 by R1 plus R2 multiplied with the input voltage. Or we can have the linear diode reference where the reference voltage is connected with the linear diode. Output switches when the input crosses the V reference. So there is a threshold level which is a V reference, and when it crosses, the output will be obtained. So again we will be getting a square wave, but in this case the output will cross the input only when V reference is crossed. So if you take one example where the resistor R1 is 8.2 kilo ohm, resistor R2 is 1 kilo ohm, and we are basically using this voltage divider reference non-zero level detection circuit. The given input voltage is 15 volt. Then the reference voltage, if we compute by this formula, we will be getting as 1.63 volt. So it means that the output is basically switching between plus minus 14 volt when the input is crossing 1.63 volt. So this reference voltage is what we need it for the output to switch between the plus 14 volt to minus 14 volt. What is noise in the case of amplifier? So noise is basically the unwanted voltage fluctuation that cause unstable switching near the threshold level. Let us take an example. A low frequency sinusoidal voltage with noise may cause erratic output. So whatever the desired output, we will not get it. So solution is to implement the hysteresis using the positive feedback. So you can compute the upper trigger point and lower trigger point, and then the hysteresis voltage will be the difference between the upper trigger point and the lower trigger point voltages. How do you compute this voltage of upper trigger point and lower trigger point? That is again with respect to the voltage division rule, where you have the plus V out maximum and minus V out maximum, which is multiplied with the resistor R2 by R1 plus R2. So this circuit is also known as Schmidt-Trigger circuit. And here the noise signal, if you can see it, the pure sinusoidal wave is basically hampered or disrupted with the noise signal, which is unwanted voltage fluctuations. So we will be getting the output voltage, which will be non-square in nature and non-sinusoidal in nature also. And hence we need the hysteresis method to get the output voltage, computing the upper trigger point and the lower trigger point. The output bonding is basically the limit where the output voltage to values less than the op-amp saturation. And the method that we get is basically two methods we can use. Either we can have single linear diode which is connected and it will bound in one direction. Two linear diode will bound in both the direction. So let us see the circuit what we have. So the bounding, whatever is formed. So this is the bounding which is founding. So a linear diode is connected between the input and the output terminal, which is connected. So linear diode may be connected in two different ways. So the first one where the linear diode is connected in the bounded at positive value, the other one is bounded at the negative value. So the other form of the network is a double bounded comparator, whether we can have the two linear diodes which are connected back to back. Then in that case, we will be getting the output voltage where we need to add the linear breakdown drop 0.7 volt. So if the example we take 4.7 volt linear, then the output will be bounding from plus to minus 5.4 volt. So this is the comparator with output bounding, where the linear diode is connected between the input and the output. The applications of comparators, two special applications we will be talking about. The first application is basically the temperature sensing, and second one is the analog to digital conversion, which is known as the flash ADC. So in the temperature sensing device, if you can say this is the circuit of temperature sensing using the comparator applications. So here we use the Wheatstone bridge with the thermistor, which is thermal resistor. In other terms, it uses the comparator to detect the breach balancing point, and it will trigger the alarm or response when the temperature exceeding the threshold level. So whenever we need to sense the over temperature, we can go with this type of comparator network, where you have basically the op-amp as one of the devices, which is the application of the op-amp circuits in the form of a comparator. The other one is basically the analog and digital to conversion, where you have parallel comparators. So you can see there lot of ADCs will be formed by connecting the op-amp in parallel with reference voltage ladder. So you have the register which is connected in the form of a ladder network, and there will be 2 to the power n minus 1 comparator needed for n bit conversion, because we are going with analog to digital. So priority encoder produces the binary output. So here we will be getting the binary output at the output of these comparator analog to digital device. So I have discussed here very basic circuit and few applications of the comparator. We can discuss more detail in a later discussions. Other circuit that we have is basically the summing amplifier, which is the application of inverting op-amp configuration. So what type of circuit we need? We need basically the inverting circuit. So we have the negative terminal here, These negative terminal are basically connected to some of the registers, and you will be getting the output which is proportional to the negative sum of the input voltages. So here we have two input inverting summing amplifiers shown, where we have input 1 and input 2, which are given with registers R1 and R2 to the inverting terminal, and there is a feedback register which is connected between the output to input. So the output voltage in general form, we have a negative because it is a inverting amplifier, and we will be getting the summation of all the inputs in the feedback form. So RF by R1 into V input 1, then RF by R2 V input 2, and so on till the last register or the last input. Generally, it is seen that the registers are basically equal. R1, R2 and Rn will be equal to R. Then in that case, the output voltage will be simplified of this general equation, which is in the form of minus RF by R and summation of all the input voltages. So this is the circuit which shows that there is a summing amplifier and there are n inputs which are given to the inverting terminal, and there is a feedback register connected. One special application of this summing amplifier, which is known as unity gain summing amplifier, where the feedback register is equal to the same input register, then in that case the output is very simple, an inverted sum of the inputs. So you have the negative sign which represent the phase difference, and this summation of V input we get at the output. So if the inputs are plus 2 volt, minus 3 volt, plus 4 volt, and so on, the output voltage we will be getting with a negative and summation of all the voltages which come to be minus 3 volt. Other type of circuit, let us see the averaging amplifier, which produces mathematical average of the input voltages. So here again we are connecting the inputs at the inverting terminal of the amplifier, operational amplifier, and let us take the RF by R equal to 1 by N, where N is the number of inputs. So here the number of inputs that we take is N, and the feedback register by the register of the input circuit will be equal to 1 by N. Then in that case, the output that we get is minus. So here 1 we are getting instead of R, and the sum of all the voltages. So if you have an example where you have 4 input averager with the feedback register of 25 kilo ohms and the input register of 100 kilo ohm, then the output voltage that you get is in the form of this equation. Okay, so you will have 4 input averager circuit where the circuit will have 4 input. Digital to analog conversion that we have seen in the previous discussion also, where we have the binary weight register DAC, or you can have R by 2R ladder DAC. There are 2 different ways by which this DAC can be formed, digital to analog conversion. So here you can see this is basically the op-amp circuit, and the input that is connected to the inverting terminal is basically connected in the form of scaling adder. Okay, so this is a binary weight. It can also be connected in the form of R to R ladder network. So these are the 2 different ways of digital to analog conversion to get it. So if we focus on binary weight register DAC, so each input register correspond to the binary weight. So here you can see the registers which are connected. So these are registers will be corresponding to binary weight, and the MSB of this small register R next will be 2R and then 4R. So this is the MSB, and then you have 2R, 4R, 8R, and so on. So output will be analog representation of the digital input. So here the input that we give is digital, and the analog output we would be getting. In the R by 2R ladder DAC, you use only 2 register, that is R and 2R. So here you have the circuit which is formed by R and 2R, and these are more practical for IC implementations. Each bit will contribute half the voltage of the previous bit. So it is connected in the form of ladder. So each bit will be contributing only half of the voltage of the previous bit, and the output that we will be getting is basically in the form of analog. When we discuss the other form of circuit of op-amp, that is the integrator, this is producing output which is proportional to the integral of the input. So we have two devices required. One is the input register, another is the capacitor. So here you can see this is the input register and there is a capacitor which is connected between the output and the input. So output voltage we will be getting as minus because it is connected to the inverting amplifier terminal. So this is 1 by R in C and integration of the input voltage. So this will have the constant input will produce the linear ramp output. So when you are giving step signal in the input, then the output that you are getting is basically in the form of a linear ramp output. So this is the integrator circuit where you require the resistor and capacitor in the network. Resistor is basically at the input terminal and capacitor is at the feedback terminal. So if you take one example where the input resistor is 10 kilo ohm, capacitor is 0.01 microfarad and square wave input that we give or the step input plus minus 2.5 volt, then the output voltage with respect to time t, delta V out by delta t, we will be getting as the minus of V in by R in C. So this is with respect to the integrator voltage equation. So if you substitute these values, known values, we get minus 25 millivolt by microsecond. So the output that we get is basically in the form of a triangular wave with 5 volt peak to peak. So the input that we are giving is basically square plus minus 2.5 volt and the output that we are getting is basically triangular with plus 5 volt peak to peak. So this is the integrator example. Next circuit, we will see the differentiator. So how it is different from the integrator is basically it produces the output which is the derivative of the input. Here also you require a capacitor and feedback resistor. Earlier we use input resistor, here we require feedback resistor. So the output that we get is in the form of a differentiation dV in by dt multiplied with RFC and the negative because we are connecting with the inverting terminal of the op-amp. So it is again producing a ramp input, produce a constant output. So here we are giving a ramp input here. Output what we get is a step. In the previous case, we gave step input and get ramp output. So differentiator will be the reciprocal of or the inverse of the integrator. So here you have the feedback resistor here and the capacitor is connected here. Remember in the previous case, we have connected a capacitor here in the integrated circuit and resistor here as the input resistor. But in differentiator, we have changed its position. The input is capacitor and the output is feedback resistor. The next circuit we will discuss is the instrumentation amplifier. These circuit amplify small signals riding on a large common mode voltages. Common mode voltages we have discussed in the previous lecture in detail, the concept of CMMR. So the key characteristic that we get in instrumentation amplifier is high input impedance, high common mode rejection, low output offset and low output impedance. So here you can see one of the basic instrumentation amplifier circuit where you have 3 op-amp. So this is op-amp 1, this is op-amp 2 and this is op-amp 3. So the input stage we have 2 op-amp. So these 2 op-amp will become the input stage and the output stage you have the third op-amp which is the difference amplifier. So you get high input impedance and initial amplification for the input stage and the output will be a difference amplifier which will subtract and amplify the input signal difference. So the closed loop gain that you get is basically 1 plus 2R by R gain because we treat all the resistors to be equal. Generally, this will be the case you will be getting where all the resistors that are connected in this network will be equal to R. In that case, you will be getting the circuit with a closed loop gain ACL is equal to 1 plus 2R by R gain of the circuit. Other one important circuit is the operational transconductance amplifier, which is basically a voltage controlled current source. This convert the differential input voltage into output current. So whatever the input you are giving in the form of a differential voltage, you are getting a current as the output. So this current as the output is basically controlled with the conductance GN and the difference voltage V positive minus V negative. So output is basically a current, unlike the op-amp where you get the output as voltage. So in the normal op-amp, we get the output as voltage, but this OTA circuit, we will be getting the current as the output, and the transconductance GM is programmable via the bias current. So bias current we have discussed, transconductance we have discussed in the fundamentals. Now, these have the key characteristic: high input impedance, wide bandwidth, linear transconductance over the bias region, and it is suitable for analog to signal processing. So, for the OTA network. And the symbol for the OTA is having a normal op-amp. And if you can see here, there is a circuit which represent the biasing current as the controlling parameter, because you have the conductance GM, transconductance, which is controlling this output, and the output that you get is basically a current and not the voltage. So the applications of these OTA are basically voltage control filters and oscillators, multipliers and dividers of analog circuit, the audio and RF processing, AGEC circuits, and function generators. And if you compare this OTA with the normal op-amp in features like output, OTA will give you the current output, op-amp will give you the voltage output. These are basically controlled with the bias current, op-amp are controlled with open loop gain. The key parameters are the transconductance in OTA, and op-amp will have the open loop gain. The primary use is tunable analog circuits, and here you have the voltage amplification as one of the application of op-amp. Other circuit, we have the log amp. These are special case of the op-amp circuits. The output, what you get is a voltage proportional to the logarithmic of the input voltages. So if you see the output voltage, it is basically the natural logarithmic of the input voltage divided by some constant Vt, which is a thermal constant. And here also a constant is multiplied, and negative sign is indicating because we are connecting with the inverting terminal. So it is based on the exponential current voltage relationship of a diode or a BJT. Now, in the very previous basic lectures of these electronics, we have discussed the diode and BJT, where we have discussed what is this thermal voltage Vt and how it plays an important role in case of a diode. So it uses an op-amp with a diode or a BJT in the feedback path. So if you see the feedback path of this circuit, either a diode can be there or the BJT can be there. So such type of network will give you the output which is having a voltage proportional to the logarithmic of the input voltage. So whatever the input voltage we are giving and the output voltage, whatever we compute, will be getting the logarithmic of the input voltage with this formula. So if for that we need a diode or the BJT in the feedback path. The anti-log amplifier, which is the reciprocal of the logarithmic amplifier, this convert a logarithmic input and it give back the linear output. So the input that we give is in the form of logarithm. And here the transistor or the BJT is used in the input path. So if you see the input path, we are connecting the transistor and it will create an exponential relationship of the output. So output what we get is basically having an exponential factor. In the previous case, we were having the logarithmic factor. So this often paired with the log amps for analog multiplication to division. So this is basically with the fundamentals that we know log A plus log B will be equal to log of AB. And if you take the anti-logarithmic of that, you will get the AB only. So based on this principle only, this anti-log amplifier is working, where the difference is we are using the BJT in the input path. So isolation amplifier is one of the circuit of the op-amp application where we transmit signal across two circuits using galvanic isolation. So isolation is required because we do not want the two circuits to be in touch with each other, and we need to transmit also the power. So it prevents high voltages or ground loop current from damaging the system. So that is the reason it is known as isolation. So isolation is achieved using transformer coupling, optical isolation using optocouplers, and capacitive coupling. So we have discussed this optocouplers also in the very initial lectures of the electronics. So the key features whatever you have is basically high input to output isolation voltage, accurate signal transmission, and the high CMR, common mode rejection. So if you see the block diagram of this typical isolation amplifier, you have the op amp, and then it is basically given to a network, which is the input stage, comprising of modulator and oscillator. And there is a capacitor which is basically disconnecting the input and the output coupling. So output you have demodulator and again the op amp circuit. So the input and the output stages are having galvanic isolation. So these isolation amplifier are having applications in medical instrumentation, industrial process, high voltage system monitoring, signal isolation in data acquisition systems. And those are having advantages because it protects measuring devices from voltage spikes. It eliminates the ground loop and the electrical noise. It enables the safe measurement in hazardous environments. So it has to be noted that often it is integrated with analog to digital converters, these isolation amplifier circuits. Some of the other circuit we will discuss, that is the constant current source, which deliver a fixed current regardless of the load resistance. So whatever the load resistance you are putting at the output, you will be getting a fixed current. So the current is basically in terms of the Ohm's law, which is I is equal to V reference by R, where R is basically what you connect at the input, and you are giving the input voltage to the inverting terminal and use negative feedback to maintain stable output current. So you need a stable output current. Load resistance can vary, so you will be getting stable current with the help of constant current source. Other circuit, current to voltage converter, it is known as trans impedance amplifier. So this again known as trans impedance amplifier, which is a current to voltage converter. So as the name suggests, it converts the input current to the output voltage. So the output voltage what you get is minus of I in RF. The negative is again the phase conversion. So it is having connected with the negative terminal and commonly used with photodiodes and sensors. So this is current to voltage converter amplifier, operational amplifier circuit. If you want to convert the voltage to current, so the input you give a voltage and you will be getting voltage control, current control sources. Convert the input voltage to output current in the formula I out is equal to V in by R, and it is useful in actuators and LED drivers. So here we are connecting the circuit of the registers, which is the load register and the R1 in the inverting terminal of the op amp, and the non-inverting terminal we are giving the voltage input. The peak detector is one of the application of the op amp where we capture and hold the peak value of an input signal. So suppose the input signal is sinusoidal. So this is the peak value of the input signal. So it will be capturing and holding it, and it is used in op amp, diode and capacitor applications, and commonly used in signal processing and instrumentation. So this is a basic peak detector circuit which is having a op amp. The input voltage is given to the non-inverting terminal. You are basically connecting a diode and a capacitor at the output to get the output and hold the peak value of the input signal. There is a reset button given in the non-inverting terminal which you can reset it. So what are the conclusions of this discussion is that the operational amplifiers are versatile component used in electronics, which enable a wide range of circuit. What are the circuit we have discussed? The comparators for signal comparison and the analog to digital circuit conversion, the summing amplifier, averaging amplifier, DAC circuits, integrators, differentiators for waveform generation, instrumentation amplifier for the precise measurement, some of the specialized circuit, OTA, log, antilog, isolation for advanced applications. So their gain is very high. Flexibility and reliability make this op amp essential for the modern electronics. And in future exploration, if you can see, these advanced op amp designs and integrations will be done with the digital system. So in the previous lecture, we discussed the basic of op amp, and here we have discussed the much detail on op amp circuit. So both the lectures will be important from the operational amplifier circuit point of view. So operational amplifiers are completed now. We will move to the next lecture in the form of active filters. Thank you for now.